Okay, in last lecture, we just discussed a little bit introduction related to the K-way merge sort. Okay, so that is two-way, three-way, and four-way. Okay, so these are the variations we have already discussed. So inside the two-way, we just perform the merging of two runs. So one run means one particular block of elements which contains the number of elements. So we can able to merge the particular contents and we can finally get the sorted output. Okay. Then in three-way, we are having the three runs that can be just merged into one. And again, inside the four-way, we are having the four runs that can be just merged into one. Okay. So we have just discussed this particular algorithm. Now, this is the particular algorithm for K-way merge. Okay, so inside that KV merge sort, what happen? Whenever we want to just sort the particular content. So in that particular case, we are having the storage on the disk. Okay, so from disk we can just feed the particular data into the internal memory and perform the sorting and again store back the sorted contents to the disk. Okay, so repeat this particular field until we can able to sort the particular content again and again. Okay, so let's see how we can able to mute your mic. When joining, you can just take care that you have to mute your mic and then join. Okay, so here we can able to consider this particular example. So such examples we can able to have inside our paper. That is consider the two runs or three runs having four records, and depending on that particular three-way merge, you can able to merge the particular content. Okay, so now here we have to just sort out the particular contents. Okay, so here this is the simple example. So let's see how we can able to consider this example in our program. Okay, so you can also take a notebook and try to solve with me so that you can able to easily get understand how we can able to perform this. Okay, so simply I just copy paste this particular content and I will just paste here. Okay, so I think it is visible to all. Okay, so here we are having this particular example. So what is my condition? My condition is to consider the three runs with four records. Okay, so this is the run one. So run means it is a simply a block of elements. Okay, so this particular run means this is the block of block having the four elements. This is the block having the four elements, and this is the block having the four elements. Okay, so in each block we are having the particular records. Okay, now we have to just perform the three-way merge of that particular contents. Okay, so here inside the three-way merge, what happened? We can consider the one particular content from each run, and we can able to combine, sort it, and again we can move proceed. Okay, so let's see how we can able to contain these particular ways inside our program. Okay, so inside our program we are having the First condition, that is we require the particular execution with three-way merge sort. Okay. Now we are having the 3 runs. So runs means it is a block having 4 elements each. Okay, particular pictorial form we can just have over here. So this is the run 1, run 2, and run 3. What is our expected output? This particular output. So this is the output which we require. Okay. So how to proceed one by one? So first step, that is consider the first element from each run. Okay. So step 1 includes the consideration of first run, that is 3, 2, 1. Okay, so first element we have considered from each run. Okay, so I just increase the size so that you can understand. Okay, so first step, what is our first step? First step is important. That is, we can just consider the first element from each run. Okay, so suppose we are having the 3 runs. Then we can just take the first element from each run. Okay, so we have just considered the first element, that is 3, 2, 1. So we just take the this 3, 2, 1 inside the particular run. Then here, this is the input. So these are the particular input. So this is the input, and here output run is there. Okay, so inside the output, from input we are having the 3 elements, that is 3, 2, 1. So this is the from first run, this is from second run, and this is from third run. Then from this, identify the smallest one. Okay, so whatever the smallest one, we have to identify and shift to the output run. Okay, so this is the particular smallest one we have identified. So we can just shift to the particular output run. Okay, then what is the next step? Whatever the particular element which is removed from that particular run, we have to just find the next element from the same run. Okay, so basically one is available over here. So we have considered this one, and this one. Okay, now we have just selected this particular one because it is the smallest one. So we have transferred to the output run. Now we have to just find the another element from the same run from which it is removed. Okay, so one is removed from run 3. So we just consider now 6. Okay, so again we are having the 3, 2, 6. Okay, so this is the step 2. Again, we need to identify the smallest one from this particular 3. Okay, so here again, whatever the smallest one is this one. Okay, so we can just shift the smallest one. So after the first element. So one is already available over here. So we now shift this particular 2 to the this one. Okay, so now what happened? We can just go inside the 2. So it is available inside the second run. So we can just select the next element as its replacement. Okay, so we consider now 4. Okay, so here step 2 contains step 3 contains 3, 4, 6. Now just find out the smallest one. So 3 is the smallest one. So again 1, 2, 3. Okay, so 3 is available inside the first run. That's why again move towards the next element from the same run. Okay, so the basic rule is whatever the elements which is transferred from that specific run, consider the next element from the same run. Okay, so for example, समजा आपण run 1 मधून एक element transfer केलाय. So we can just find the another next element from the run 1 itself. Okay, so we just again find the 5. So inside the step 4, we just find 5. So 5, 4, 6. Now again identify the smallest one and just transfer it to the particular run. Okay, so here we just identify this particular. So we can just transfer to the next element. So we consider the 10. So step 5 having the 5, 10, 6. Okay, so again identify the smallest one. So we can just go inside the output run as 5. So just identify the smallest one. So from this particular smallest one, we can consider the next element, that is 12. So here again step 6. So instead of 5, we can just replace with 12, 10, 6. So what is my output run? Output run is now identify the smallest one. So smallest one is 6 1. So 1, 2, 3, 4, 5, which are already available. So now 6 is transferred. Okay. Now here I just consider this particular 6. So now goes to the next element in the same run. So I just consider the 8 instead of the 6. So 12, 10, and 8. Now again, identify the smallest one. So smallest one again from the same run. So we can just move towards 1, 2, 3, 4, 5, 6, 8. Okay. So for this particular 8, again, we have to just move towards the next element from the same run. So step 8, 12, 10, and element is 18. Okay. So from these particular elements, again, find which is the smallest one, this one. Okay. So we can just move towards this particular 1, 2, 3, 4, 5, 6, 8, and 10. Okay. So again, search for the particular next element from the same run. So after 10, we are having the 17. So we can just coming with that particular element. Okay. So 12, 17, 18. So from that particular, again, we can just identify the smallest one. So again, we just transfer to the output run. 5, 6, 8, 10, and 12. Okay. So for 12, again, we can just identify this and we can just find the next element. So 12. So 12 is already transferred. So next element is the 15. Okay. So 15, 17, 18. So now what happened? We need to move this particular to the another. So here identify the smallest one, that is 15. So we just move that 1, 2, 3, 4, 5, 6, 8, 10, 12, and 15. Okay. So after 15, there is no element remaining. So only two elements are there. So inside the step 11, we have only 17 and 18. So after 17 also, we don't have any element. After 18 also, we don't have any element. So directly, we can just transfer that particular elements. So identify the smallest one, transfer it. Okay. So here I have just transferred the 17, and then after this particular 17, 18 is there. So 17, there is no element. So we can just directly move towards the step 12. So we can just identify 18. So again, there is no another element. So we can just transfer 18 to the output run. So 1, 2, 3, 4, 5, 6, 8, 10, 12. Then 15, 17, and 18. Okay, so this is how we can able to transfer the particular elements with the help of the three-way run. Okay, so this is how we can able to transfer the particular contents using the three-way runs. Okay, so what we are doing, I am just again repeating. First, consider the each element, first element from the each run. Okay, because we are having the three-way runs. So three-way runs means what? There are three runs having the number of records. So that particular data is already given. The numbers are given. So what is our expected output? We need to sort out that particular elements. So first, we just take the all first elements. So 3, 2, 1. So we just take these three, then identify the smallest and move towards the output run. Then whatever the elements which are transferred from same run, consider the second element. So one is available inside the run 3. So we can just move towards the next element from the same run, that is 6. Okay, so we just replace that particular one with 6. Again, we can just find the smallest one. Again, we can just move towards the next and so on. Okay, so these are the total 12 steps which are used to just sort out the particular elements with the specific run. Okay, so this is how we can able to just solve the particular problem. Okay, so in exam there may be a question that is consider the 2 runs with 3 records, or consider the 4 runs with 5 records. Okay, so in that particular case you can just plot that particular runs, and depending on that run you can able to just uh, write the input run and output run, and what are the contents inside the input run, and what are the contents inside the output run. Okay, so that you can just able to easily sort out the particular elements by just considering this particular mechanism. Okay, so clear? Just put the message in the chat, yes or no, or if you have any doubt you can just on your mic and just tell me.
Sir,
Yes.
I have one doubt. हॅलो
हा.
सर, जर तिथे दोनच रन्स असले तर तुम्ही फर्स्ट स्टेपला फर्स्ट इलेमेंट कन्सिडर केला ना, तर दोनच कन्सिडर करायचे का?
नाही, आता if we are having the 2 runs, then whole elements which we want to sort into the 2 parts.
ओके.
Okay, आता समजा same example आहे. So for example, I will just show you. Suppose we are having the 2 runs having 6 records. Same example. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So run 1 contains. So this particular data requirement is already given by the particular program itself. Okay. So it may be 3, 5, 2, 4, 12, 15. And run 2 contains maybe 1, 6. Here it is a sorted order. So 2, 4, 3, 5. Okay. Then 1, 6, 8. Then 10. 15. And 15 is already there. So 17 and 8. Okay. So this requirement is already given. So in that particular case, what we want to do? We have to just apply the same logic. We have considered the first element from the 2 runs. So now my array is 2, 1. So just find the smallest one. So transfer to the output run. Then from the same run, we can just shift to the next element. So now I just take 2, 6. So now 1, 2. Then again from this, we can just shift to this. Then we can just move towards the same fashion like this. Okay, so depending on the example, you can just clearly read the particular contents. Okay, so how many runs are there and which sorting technique we need to apply. Okay, so if 3 runs are there, we need to apply the 3-way merge sort. Runs are there, we need to apply the 2-way merge sort. If 4 runs are there, we need to apply 4-way merge sort. Okay, so depending on the sorting technique, we can able to just apply the same logic with number of runs. Clear?
Yes, sir.
Anybody else? Whichever the doubts, you can just clear it, no problem. Because such examples in exam, there may be a 8-mark example is there. So if you understand the logic, you can easily get the particular contents. So only
Hello?
part is that you have to just follow the logic.
Hello?
Yes. Yes.
Yes. If input runs are of different size, it is applied.
Yes. So here the requirement is not having the differences. Suppose I am just attaching the one more record over here. So after 17, I just attach 20. So whenever we just stop at the 17 instant. Okay, so here. So after 17, there is no elements. That's why we are not replacing the particular element. But here, suppose after 17, 20 is there. So I can easily write 20, 18. Okay, then identify the smallest one, and then I can just having the only one element, that is 20, and I can just apply that particular after the specific run which is available. Okay, so after 20, after the 18, I can able to add the specific content in my program. Okay, so here you can just take any thing whichever you have. So it doesn't matter that you want the particular specific number of elements in the same run. Whatever the number of elements, you can just continue and you can just stop whenever the elements are empty. Okay. Anything else?
Sir, here all the runs having ascending order. Then if there are unsorted runs?
No, unsorted runs are not used inside this particular external sorting technique. So whenever we are considering the particular elements, that must be in ascending order itself. So this is the prerequisite. So whatever the runs you have, that particular runs must having the ascending sorting elements. Then only it will applicable. Else we are not able to sort the particular elements by using the merge sort.
Okay, sir.
Yes, anybody else? So if you understand this particular example, you can able to solve any particular example with 2 runs, 3 runs, 4 runs with different records. So that you can able to easily convert any particular example into the sorting. Okay, so you have to just remember these particular steps. So first step, you can consider the first element from each run. Then identify the smallest one, transfer to the output run. So whatever the run from which we can just transfer the run, find the second element from that same run. Okay, so this much logic we have to apply inside our program. That's it. Clear?
Clear, sir.
Okay. So this is the simple example which we can just see. So whatever the description related to this, you can just observe that particular description over here. So whatever the PDF I have just provided. So whatever the highlighted part I have just highlighted with the marker. So whatever the concept I have told, that particular concept they are just writing in the written description. That's why it is a little bit tough to understand. So that's why I just take that particular example in this particular format. So 12 steps are there. So all that particular steps that are written in the sentences. Okay. So next one, that is the buffer handling for parallel operation. Okay. So inside this particular, again, suppose if we use the buffer handling mechanism. Okay. So buffer handling means what? We can able to just store the particular data into the temporary storage, which is called as buffer. Okay. So the K-way merge sorting techniques, whatever they discussed in the previous section, we can just discuss that particular technique using the buffers. Okay, so within that particular same technique, we need to use the particular buffers. Okay, so this particular buffers. So inside the K-way merge sort technique, we need the K inputs and one output buffer. So here, in that particular example, we can just consider the K input buffers, that is K-way run merge sort, and one output buffer is available. Okay, so whatever the read operation, merge operation, and write operation requires this particular disk access. Okay, so here load the record into the runs from the input buffer, perform merge operation on the input buffer, store the result onto the output buffer, and again transfer the particular record from output buffer to the disk. Okay, so this particular operation requires some time. So instead of doing that, we can perform the whatever the read, merge, and sort or write operations simultaneously. So that's why we can just use the buffer handling mechanism. So inside the buffer handling mechanism, what we want to do, we want to just do or perform the two output buffers. Okay. So just mute the mic wherever it is. Nehalata, you just mute the mic.
Yes, sir.
So while attending the lectures, you just take care that do not on the mic. So here inside this, inside the particular merge sort with buffering mechanism. So now we just have the particular 2K input buffers and 2 output buffers. Now inside the previous example, what happened? We are having the K input buffers, K input buffers and one output buffer. Now here to perform the operation simultaneously, what is our condition? We require 2 K input buffers and 2 output buffers. Okay, so let's see the example related to this also. Now here we need to perform the two-way merge. Okay, so two-way merge means what? The value of K is 2. Okay, so 2 into 2, that is 4 input buffers. So here 4 input buffers are there. And we can consider 2 output buffers. So 2 output buffers. Okay, so here that particular arrangement is done over here. So this is the row for input, this is the row for output. Okay, so again the block size is 2. That is, each run or each buffer can hold the 2 records. Okay, so this is the first buffer having 2 records. This is second, third, and fourth. So this whole row is of input buffer. Again, this is having 2, this is having 2. So 1 and 2. So these are the output buffers. So this is my first condition. Okay. So what is my requirement? I want to just sort that particular by using, yes,
Screen it is not visible, sir.
it is visible.
Yes, sir, it's stuck.
So just check.
Still not visible, sir.
Share that. Now check.
No, sir.
Now is it visible?
Yes, sir.
Yes.
Yes, sir.
Yes.
It's visible.
Okay. Okay, so PDF is visible or not?
No, sir.
No, sir.
No.
PDF is not visible. I have shared a whole screen. So just tell me whether it is visible now.
Yes, sir. PDF is visible.
Yes.
Okay.
Not visible, sir.
It not visible, sir.
It is visible.
It's visible for my side.
Visible, sir.
Whenever you don't have any visibility, you just leave the meeting and again rejoin or refresh the particular team so that you can able to just visible that. Okay. So here, what is our first step? So here inside the merge sort, we need to apply the buffer handling mechanism. Okay, so what is our basic condition? We need to just handle this particular 2K input buffers and 2 output buffers. So output buffer size is fixed, that is 2. Input buffers, that is whatever the KV merge sort. So whatever the value of K into 2. Okay, so here value of K is 2. That's why we just having the 4 input buffers and 2 output buffers. Okay, so all that particular buffers we have organized in this particular fashion. Okay, then here this is the first run, this is the second run. Now what is my requirement? We need to consider that block 2 at a time. Okay, so here in previous example, what we are doing, we have considered only one output buffer. That's why we can consider only one input, one element at a time. Okay. Now here 2 output buffers are there. So you just might observe this particular content. That is 2 output buffers. So from each run at a time, we have to consider the two elements at a time. Okay, so first of all, I want to consider the first run, that is 2, 4, and the second run having the 2 elements, that is 3, 5. Okay, so same contents I have just considered here. 2, 4 I have considered. Again, I have considered the another element, that is 3, 5. Okay, so why we are considering the 2 elements at a time? Because the output buffer having the capacity of 2 elements. Okay, so here first 2 elements from the first example, that is 2, 4, and second run having the 2 elements, that is 3, 5. So we have considered that particular, and we can able to just sort that particular elements. Okay, so same elements we can just consider, and whatever the contents from this particular elements, we can now shift to the next element. Okay, so let's see that particular example on the board so that you can able to understand that. Okay, so I will just shift a little bit. Okay, so same example, I will just copy paste from the contents. Okay, so now we have to just consider the output contents. So here I will just predict the input. So input 1, then input 2, input 3, and input 4. Okay, so little bit delay due to the network is there. So okay, so input 1, output 1, and output 2. So each particular buffer having the two elements. So input 1 having 2, input 2 having 2, 3, and 4. And again output having this particular. So this is my initial condition. So now what happened? I want to just take the first two elements. So 2, 3 I have just taken. Then so this is the first run first. So these two elements for the run first. Okay. This is for run 2. Because what is our task? Each buffer can hold 2 records and block size is 2. Okay. So block size is 2, that is for each run there are 2 blocks and each block contains the particular 2 records. Okay. So that's why we just take this particular. So I am just considering this particular 2, 4 and 3, 5. So this is the initial condition. That is at a time I have just loaded the 2 contents from the input. So why 2 contents? Because we need to just output the particular 2 elements at a time. That's why we just consider the 2 elements, 2 inputs at a time. Okay. Then parallelly, we want to just search from that particular elements. So what is our next step? We have to just identify the 2 elements which are smallest. Okay. So 2, 4, 3, 5. So which are the smallest element? That is this particular 2 and 3. So these 2 elements we can just sort out and just include it inside the output one. That is inside the output buffer. Okay. Now, what is our condition? We are having the particular condition, that is 4, 5 and 2, 3. Okay. Now what happened? We need to just load the another number. Okay. So from this particular input, we consider the next run, that is, so one element is already removed. Okay. So this particular element we have removed, but this particular element is still present. But we need to replace this with the another, that is 6, 8 and the 760. Okay, so now I'm having this much records available. Okay, so from this particular record, again I have to shift this particular whatever the smallest element. So smallest element is 4 and 5. So shift this same element over here, 4 and 5. Okay, so now my contents are 6, 8, 7, 6. Because at the time we are having the parallelism. So buffering mechanism is there and we can apply the parallelism inside that. So at a time we can just perform the two operations, that is input as well as output. Okay. Now whatever the contents which are available inside the output run, we can just store inside the disk. Okay. So inside the disk we can already store 2, 3, then 4, 5. Okay. So now we can just sort out the particular content from this. And we can load the next set of the elements, that is 9, 6, that is 9, 10, 6, 8, and again 12, 21 and 26. So from these all elements, we need to identify the smallest one. Okay, so smallest one is this one and this one. So we need to just find out inside the particular output. Okay, then after that, we just move towards the output. So 2, 3, 4, 5, 6, and 7. So again, we can just identify the smallest one, that is 8 and 9. So we can just shift to the 8 and 9. Again, we can just identify the smallest one, that is 10 and 16. So we can again 10 and 16. And after that, we can just identify the last one, that is 21, 26. So final output is 2, 3, 4, 5, 6, 7, then 8, 9, 10, 16, 21, and 26. So same thing that are given inside the program as a 7 steps. Okay. So same example we can just have available over here in each step. Okay. So whatever the steps we just discussed, each step and its discussion that is given inside the program. Okay. So here, instead of the one element at a time, we can just shift the two elements at a time. And contents and elements inside the input key, and again we can load it. Okay, so input having the two elements at a time, output also having the two elements at a time. Okay, so this much change is only available inside the program. Okay, so again, suppose if the 3 runs are there, you can load the 3 elements at a time. If 4 runs are there, you can load the 4 elements at a time, and so on. Okay, so depending on the particular runs, you can just consider the particular input. Okay, so here we are having the two-way run. So we can just take the particular elements. Here, output contains only 2 elements. That's why we can just load the 2 elements at a time. If we are having the 4 runs, then we can consider the particular contents from each run and we can load the particular elements. Okay, so in this way, we can able to handle the different operations. Okay, so same example with KV search that are given over here. Okay, so you can just read these particular steps and you can just find whatever we just discussed over here. So same way, we can able to apply to this particular k number of particular buffers. Okay, so in this way we can able to find the buffer mechanism for the particular KV merge sort technique. Okay, so input buffers, output buffers are only 2. Okay, so if you can convert this same example into the 3-way, what is the difference? You just tell me. Suppose I am just converting this particular, instead of the 2-way, I will just consider the 3-way. So what happened in that particular?
3 inputs are
Number
there.
of blocks will be increased.
3 inputs are there, sir.
Here,
Okay, 3 inputs are there. But what is the output size?
3.
2.
2 buffer of 3 size.
Yes,
Yeah.
2 buffers having the size of records is 3. Okay, so how it will just convert? It will just convert this whole input into the 3. Again 3. 3 1. That is extra one. Okay. Then again here 3. Again here 3. So how many inputs buffers are there available? 4 or 6?
6 buffer.
6.
6 buffer, because we just consider 2k. That is 2 into 3. That is 6. So again 2 more are available. And output buffers are only 2 because we just consider only 2 output buffers. So here having 3 records, having 3 records. Okay. So from each buffer, we can just consider the 3 elements at a time and we can able to just handle the operations on it. Okay. So in this way, we can able to sort the particular elements by using the buffering mechanism inside the same merge sort. Okay. So this is the example which is explained inside the book. Okay, so all the steps, whatever we just discussed, same steps that are discussed in the program. Okay. Now, next part, that is Okay. So now next part that is related to the floating buffer concept. Okay, so floating buffer means what? Here, whenever the particular size of the buffer is large. Okay, so inside that we can not able to just handle that particular size with number of the particular buffers are added. Okay, so for example, suppose if I am having the 10 buffers, then it is not possible to just utilize all the 10 buffers at a time. So whatever the spaces which are available, so you might observe that at one instance, these particular contents are empty. Okay, so for example, only first element from the first input is allocated. But what about others? Okay, so other part is not able to just allocate, is not able to just able to available. So these particular things are empty. Okay, so again, this particular space is empty, this particular space is empty. So okay, so to avoid such free spacing related to this, then we can just use the particular KV merge with floating buffer concept. So floating buffer means what? Whenever we want to just require to add the particular elements, then we can consider that particular elements with additional extra linked list array which is available. Okay, and we can just connect that particular elements with the additional array, and whenever the allocation is finished, we can just delete it. So same logic we can able to apply to our program. Okay, so let's see. Let's consider the example related to the floating buffer. So here inside this, is my screen is visible?
Yes, sir.
Okay.
Yes.
Now the next part, that is how to apply the particular buffer concept to the floating buffers. So floating buffer means what? Whenever there is a requirement, we can able to add the particular buffers. Okay, as a linked list. Okay, so instead of allocating the number of buffers randomly, we can just consider the only fixed type of buffers, and whenever the requirement is there, we can able to add that particular buffers. Okay, so initially we just take run 1, then run 2, run 2 and output. Okay, so each having the size as 2. Okay, since there are the 2 runs, so we can just take the so do not unmute your mic, whoever it is. You just take care of that. So here we can just consider the particular first element from the first run, first element from the second run. Okay, so here I just consider 2, 4, 3, 5. Now from this you can just identify which are the less elements, that is small elements, so 2 and 3. So I just shift that particular elements to the output run, that is 2 and 3. Now next element I want to just load 6 and 8. Okay, so 6 and 8 I want to load, but what is my condition? I'm just having only one space available. So in that particular case, I have to attach one more to that. So I can just attach 6 and 8. So this is the dynamic allocation. Now, again, I have to consider and attach here. I'm having the 5 as an element. So now you can consider the whatever the smallest element. So 4 and 5 are the smallest. So I just shift to this and now add the this particular second as element. So I just add this particular 7 and 16. Okay. Now you can consider the smallest one. Okay. So smallest one is this one, that is 6 and 7. So I can just able to shift that 6 and 7 and add the next element. So next element is this one. So I can having the 8 where we can able to attach the 9 and 10 and here 16 and we can able to attach the 21 and 26. Okay. So now identify the smallest one. So which are the smallest one? 8 and 9. So I can just add that particular 8 and 9. Again, here after this there is no element. So we can just have the empty element. So I'm having the 10, then 16 and 21, 26. Now I want to just identify which are the smallest element, 10 and 16. So I can just simply shift 10 and 16. So which are elements which are remaining, that is 21 and 26. So I can now identify this 21 and 26 and now I can just sort that particular elements 4, 5, 6, 7, 8, 9, 10, 16, 21 and 26. Okay, so this is how we can able to identify the particular sorted elements from this particular floating buffers. So floating buffer means what? Whenever space is less, we can add the extra buffer. Whenever space is not in use, you can delete that particular buffer. Okay, so this much is the additional concept inside the buffering. Okay, so whatever the buffer mechanism, we can able to apply whenever it is required, and whenever it is not required, we can just delete that particular space. Okay, so this much only difference that are available inside the floating buffer concept. Okay, clear? So in
Yes.
book also the example for, so this is the example for 2 runs. Inside the book there is also example given for the 3 runs. Okay, so this is the second example. So you can just study on your own. So 3 runs are there, and we can able to just sort that particular by using the floating buffer concept. Okay, so this is the example in which we can just use the floating buffer. So 3 floating buffers we can just able to add in each run, and we can able to sort the particular contents. Okay, so in similar case we can able to just write the particular sorting by using the mechanism called the buffering. Okay, with floating buffers. So floating means, the meaning of floating buffer means it will be just allocated based on the requirement and deallocated whenever it is not required. Okay, so these are the particular contents related to the buffer. Then next one, that is the run generation by using winner tree and loser tree. So what is meant by winner tree and what is meant by loser tree? So winner tree means what? It is a complete binary tree which help us to obtain the smallest key from the set of keys where each node represents the smallest of its children. Okay, so root node consists of smallest value whichever available in the child node, and loser tree means what? Or so loser tree means what? The tree having the largest value in the root. Okay, so let's see the example related to it. So here consider the merging of 4 runs by using the winner tree and loser tree. Okay, so let's see the winner tree. So we can consider this particular one run. So this is the one run, this is the another run. Okay, so I can just consider this particular one run, that is 15. So from each run, I'm just considering one element, that is 15, 10, 24 and 8. Okay, so 15, 10, 24 and 8. So whatever the smallest element, I can just put inside the particular root element. Then whatever the smallest element, I can just put inside the root element, and whatever the smallest element, again it will just put inside the root element. So this is the mechanism. Okay, so similarly we can able to sort the particular elements by using the, or by constructing the winner tree as well as the loser tree. Okay, so here we can able to just perform the operations step by step for generating the winner as well as loser. Okay, so here whatever the element which is in the root. Okay, so here 8 is the element which is happen inside the root. So we have to remove that particular element and add to the output run. Okay, then replace that particular with the another element from the same run. Okay, so let's see the example related to it. Just 1 second. Okay. So this particular example again, very much simple. If you observe that particular example, you can able to just understand this particular element. So detailed steps are not given in your example. So let's see how we can able to perform that particular steps. So I will just simply copy that particular and just take okay. Okay, so winner tree means what? The tree in which we can able to just identify the smallest element from the root child and just add it to the root node. Okay, so first we need to construct the winner tree. Okay, so in the step 1, I will just write stepwise. Okay, so I just identify the first each element from each run. So 15, 10, 24 and 8. So 15, 10, 24 and 8. Okay, so from that particular, I can just identify the smallest one. So smallest one is 10. So I just take it. Again, from this two, smallest one is 8. Where is it? Such distractions are pathetic. Okay. So from this particular 2, that is 10 and 8, smallest is 8. So now whatever the root element, you have to just remove.
रोट नहीं ना उन्हें रूट बोलने लगे
Nargis Mullah. Okay, so from this particular, whatever the root element, I just remove and add to the output. Okay, so my output run is now 8. Now the step second, that is whatever the 8 is removed, so I can just switch to the next element from the same run. So 12. So now instead of this particular 15, 10, 24 and 12. Okay, so now again we can just see whatever the 10 and 12 and the root element is 10. Okay, so now this particular element we need to remove and add to the our output. Okay, so again we just construct this particular graph. Now 10 is removed. Okay, so next step, we need to just add next element, that is 18. So I can just write again 15. Instead of 10, I just take 8, 18, 24 and 12. Okay, so from these two, smallest is 15, 12. Again 12. Okay, so these particular steps I need to follow. Again 12 we have to just remove. So my tree is 8, 10, 12. So from that again 12 is removed. So again, we need to move towards the next element, that is 16. So inside the step 4, we need to consider 15, 18, 24, and 16. Okay. So from this, again, minimum 15, from this minimum 16. So again, 15 is the smallest, so we need to remove that. So 8, 10, 12, 15. Okay. So this particular 15, again, we can just remove. So whatever the next element from the same run, we have to consider, that is 25. So in this way, we can able to step forward. Okay, so whichever the smallest element, we need to just remove, and we can just go forward and forward, so that we can able to just consider the particular content. Okay, so here 15 is removed. So again, we in the next step, we just consider, instead of 15, I just consider 25, 18, 26, and 16. So again, 16, 18, and from that, I just identify the 16. So 16 is added. Okay. So again, 16 is get removed. So 16 is available inside the this particular. So instead of 16, I just write the 28. Okay. So in this way, these particular steps that are continue up to the each and every element which is available inside the winner tree that can be just sorted. So this is called merge sort by using the concept of winner tree. Okay, so winner tree means what? We can organize the particular elements into the tree format. So at the initial stage, we can take the first element from each run. So this is the first element, this, and then identify the smallest one, add to the root node. Identify the smallest one, add to the root node. Again, identify the smallest one, add to the root node. Okay. So whichever the root node identified, we have to just remove it and add to the output. Then consider the next element from the same run from which it is removed. So 8 is available inside the run 4. So we just consider it 12. Okay. So again, we can just continue the same logic up to we can able to sort the particular elements again and again. Okay. So this is how we can able to just complete the operation by using the winner tree. Clear? Is there any doubt?
No, sir.
Okay. Then we can able to consider the loser tree. Okay, so loser tree having the also having the same concept. Okay, so the loser tree in which the number of comparisons are reduced. Okay, so winner tree can be restructured in such a way that instead of placing the pointer to the winners as an internal node, the pointers to the losers can be placed as a internal node. Okay, so such trees are called as loser tree. So special node is added on the top of the root node to represent the overall winner of the tournament, and that particular element we have to remove. Okay, so here So 15, 10. So 15 is a overall winner. Then from 24, 8, 24 is the overall winner. And from this particular 15 and 24, we can consider these particular winners. Okay. So in the first step, the overall winner is the output. So therefore, so we just see this particular example. So the internal node 15 and 24 represent the losers. So losers between these four elements, that is 15, 10, 24 and 8. Okay, so from that, the root node consists the loser of the winner node, that is 10 and 8. Isn't it? So that's why these elements we can able to just organize in this particular fashion. Okay, so let's see here. These are the first element from each run. Okay, so from that, who is the winner is the whatever the greatest number is the winner. So from this particular 10, 15 and 10, 15 is a winner. From this 24 to 8, 24 is the winner. Okay, so whatever the losers, so identify the losers. Okay, so loser is 10 and 8. Okay, so these are the losers. So from these two losers, you can just add the second largest to the root element, and you can just create one more element which is a special to just identify the loser. Okay, so from this particular 8 and 10, we can just compute 8 as a loser. So that particular 8 is represented over here. So this particular process repeatedly performed. Okay, so from this particular 8, we can just remove this particular 8 from this. Again, instead of 8, you can just add the second number from the 8 run, that is 12. So here I can just add the 12. So again, from this particular 15 and 10, 15 is a winner, 24 and 12, 24 is the winner. So who are the loser? That is 10 and 12. So that particular 10 is represented over here, 12 is represented over here. Again, 10 is get removed. Okay, so after 10, we can able to add the 18. So 18 is replaced over here. So from 15 and 18, 18 is the winner. From 24 and 12, 24 is the winner. So who are the loser? 15 and 12. So here 15 and here I can write, able to write the 12. Okay, and from this particular structure goes further and you can able to add the particular contents like this. Okay, so since same structure we can able to just draw by using this particular concept. Okay, so similarly we can just copy this same example and write it with the loser. Okay, so here first of all we have to consider the loser tree. Okay, so loser tree, what is the criteria? We can consider 15, 10, 24 and 8. So while constructing the loser tree, we have to consider the whatever the largest number. Okay, so 15 is the largest, so he is the winner. So 15. Then 24 and 8, largest, find the largest, that is 24. So these are the two winners. Now find the losers. So 8 and 10, these are the losers. So they are organized like this. 8. So whichever the last loser, I can just remove and add to output. Okay, so 8 is added to the output. Now consider the next element, that is 12. So I can just write 15. So this is the first step. This is the second. 15, 10, 24 and 12. So from that, just find the largest one. And after finding the largest one, just search for the losers. So 12 and 20, so 12 and 10. So just remove this, add it to the particular output queue. Again, 10 is get removed, so 18. So I can just again write 15, 18, then 24, 12. Okay. So from that, 18 is the winner, 24 is the winner, and just identify the losers. So I can able to 15 and 12. Okay. So 12 get removed. So 8, 10, 12. So 12 is removed from this. So I can just shift to the next. That is 15. So again, 15, 18, 24 and 16. So from that again identify the winners and just identify the losers. So 16 and 15. So whatever the element, we can just remove 12 and 15. Okay, so 15 get removed. So we need to just identify the next element from the same queue. So 25, then 18, 24 and 16. So again, we just identify the largest numbers and we just identify the losers. 18 and 16. So we can just write 8, 10, 12, 15 and 16. Okay, so this way we can continue the operations up to last. Okay, so after this particular lecture, you can just point it out the particular example and you can just solve that particular example so that you can able to rigorously practice that. Okay, so based on this particular example itself, we can have the particular test. Okay, so ISC is based on these particular examples. So values are changed, runs are changed, and you need to sort out the particular elements. So clear the logic for winner tree and loser tree?
Yes, sir. Clear.
Yes, sir.
Yes.
sir.
Yes, sir.
Now, next one, that is how to optimize the particular runs.
Hello.
Okay, so here, whatever the structure we are just designing. So how to decide whether that particular structure is optimized or not? Okay, so suppose I'm having the two-way merge and I am just organizing the particular elements like this. That is 3, 6, 8, 14. Or in this particular way also I am just organizing. Okay, so I don't know whether this particular structure is optimized or this one. Okay, so for that we can able to use the WEPL. So WEPL stands for weighted external path length. Okay, so weighted external path length that can be just calculated by using the weight of external node into depth of the root node. Depth of the node from the root. Okay. So suppose I want to just calculate the particular weight, then I just consider the levels 0, 1, 2 and 3. Okay. So this is the depth, and weight means whatever the number of the particular node. Okay. So here, suppose I want to just calculate the weight for this particular. So I can just use 3, 6, 8 and 14. Okay. So these are the numbers. Then depth means what? This is at the third level. So I can just consider this particular 3 and 3, because 3 and 6 are the third level. Then 8 is at the second level. So we just use the second. And 14 is at the first level. That's why we just consider 1. And we can just calculate the particular summation of each, and we can just calculate the value. Now suppose I am organizing the particular way or elements like this. So this is the 0, first and second. So each element at the second level. So I can just write 3, 6, 8 and 14. And these are the 2. That is second level. So the value is 62. So which organization is better? Particular, because we have the WEPL, that is weighted external path length, is 57 for the A part and 62 for the B part. So that's why whatever the organization of the elements, by using the first way, it is optimized. Okay, so for calculating the optimization of that particular elements, we can able to write the elements like this. Okay. Then with the help of this particular, we need to design the Huffman code or Huffman tree. Okay, so Huffman tree is nothing but the tree in which we can able to perform the particular contents. Okay, so left node we can represent with the 0 weight, and right node we can represent with the 1 weight. Okay, so now we need to construct that particular Huffman code. So inside the Huffman code also, again, the left element is less and right element is greater. Okay, so Huffman code we can able to represent by using this particular structure. Okay, so left represented by 0, right represented by 1, left represented by 0, right represented by 1. Okay, so whatever the root element value, so it is less than root and it is greater than root. That is left element and right element. So such combination we can known as Huffman code or Huffman, the tree with Huffman code. Okay, so let's see how to design that particular tree, which is called as Huffman tree. So while designing the Huffman tree, we can able to just consider this example. Okay, so I'm just copy this particular example. So this problem also, it is given in the exam, that is design the Huffman tree for the said input. Okay, so this is the example, that is consider the 6 characters, that is Q1 to Q6, having the particular 4, 6, 8, 9, 15 and 28. So this is the Q1, Q2, Q3, Q4, Q5 and Q6. And we need to design the Huffman tree. So Huffman tree means what? The tree with whatever the particular content. So whatever the root leaf node contains the elements, and whatever the left part having the weight 0, right part having the 1. Okay, so this is the construction. So how to construct that particular values? So let's see step by step. Now, first consider the first two elements, that is 4 and 6. So just organize that particular 4 and 6 and just add that particular numbers, that is 4 and 6 is the 10. So I just add the 10. Now consider the another two elements, that is 8 and 9, and just construct the particular elements. So 70 is the addition. Okay. Now we need to add the 15. Okay. So 15 is again less than this. So we need to add inside this particular node. Okay. So now we just consider 4, 6, 10. Now here I want to add the another element. So that is 15. So whatever the addition of these two is the 25. Okay. So this is the third step. So this is the first, this is the second, this is the third. Now what happened? I want to add this particular 28. So again 28 is less than this particular 17. Okay. So we need to add the this particular 17 and we need to attach over here. Okay. So at this particular level, we need to add it. Okay. So how to construct? That is 4, 6. So which is constructed 10, again 15, which construct the 25. Now we want to fit this particular. So 17 and 25. So 17 we just added over here. Okay. Then 8 and 9, which is less than this. So again we just add over here 8 and 9. Okay. And whatever the combination we can able to add over here. So what will be the value? That is 42. So now we have just merged all this particular, that is first this one, then this one to this. Again, we need to add the 28. So 28 we just search where to fit. So again it is fit over here or here also. Okay. So we need to add that particular over here. So I can able to construct the same tree 4, 6, 10, 15, 25, then 17, 8, 9, then from that 42, and here I can able to add the 28. And whatever the addition is 70. So this is called as Huffman. Okay. So here this is the Q6. This is the Q3, Q4, then Q1, Q2, and Q5. Okay, so just remember this. So here we need to calculate the Huffman code. So Huffman code, how to calculate? Just by assigning the 0, 1, 0, 1, 0, 1. Okay. So here I can just assign that particular. So left is assigned as 0, right is 1. 0, 1, 0, 1. Again 0, 1, 0, 1. Now suppose I want to calculate the Huffman code for Q1. I just use another color. Okay, so Q1. So what is the Q1 value? So it will just only a path from the root node. Okay, so whenever I want to go inside the Q1 from the root node, then what is the path? 1, 1, 0, 0. So my code is 1, 1, 0, 0. Then Q2 is equal to, what is my code? 1, 1, 0, 1. Okay, so 1, 1, 0, 1. Then Q3, I want to go over here. That is 1, 0, 0. So Q3 is 1, 0, 0. Q4 is 1, 0, 1. So 1, 0, 1. Q5 is 1, 1, 1. And Q6 is 0. Okay, so this is how I can able to construct the Huffman tree, and I can able to calculate the codes related to the each character. Okay, so suppose I am having the Q1 to Q6 characters, then I can able to design first Huffman tree, and I can able to just assign the weights. Left is 0, right is 1. And depending on that, I can able to calculate the code for each character. So how Q1 is calculated? So Q1 value is 4. So 4 is located at this particular location. So whatever the path from the root node, that is 1, 1, 0, 0. So it will just give over here. Then Q2 means 6. So 1, 1, 0, 1. Then again for Q3, that is 8. So it will be 1, 0, 0. Then for Q4, 1, 0, 1. Then for Q5, 1, 1, 1. And for Q6, it will be just 0. Okay. So this is how I can able to design the Huffman code, Huffman tree, and from that tree, I can able to just write the Huffman code. Huffman code. Okay, so such examples that are appeared in the particular ISC. Okay, so next week I'm just taking the ISC on Saturday. So at that time you have to just practice these particular examples. So total 5 examples we have seen.
Sir,
One, yes.
I don't understand how Q1 is equal to 1100.
So where is the location of the Q1? Q1 is over here, right?
Yes, sir.
Yes or no?
Yes, yes.
Yes. So what is the value of Q1? आता Q1 हितच आहे कशावरून? तर आपण Q1 ची व्हॅल्यू काय लिहिल्या?
4.
4. So that is given over here. Okay. So 4 is located at this particular location. So you can just simply find the path from root to the up to 4. Okay. So आता 4 ला यायचं असेल तर पाथ कुठून येणार? इकडून तर कुठे येणार नाही, इकडून येणार. ओके. सो हा पाथ आला, बरोबर. पाथ एकच आहे ना तो Q1 वर जाण्यासाठी.
ओके ओके.
सो आता 70 पासून आपल्याला 4 पर्यंत जाण्यासाठी हा एकच पाथ आहे. सो प्रत्येक पाथचं वेट कॅल्क्युलेट करायचं. आता ह्याचं वेट किती आहे? 1 1 आहे. देन 1 1 आहे. 0 आणि 0. सो सेम थिंग आय कॅन जस्ट राईट ओव्हर हिअर.
ओके ओके सर.
आता Q2 असेल तर Q2 पासून दॅट इज 70 पासून 6 पर्यंत यायला काय पाथ आहे? तर एकच पाथ आहे हा. सो आय एम हॅव्हिंग दिस पाथ, दिस वन. ओके. सो फर्स्ट कुठला आहे? 1 आहे. नंतर सेकंड 1, 0 आणि परत 1. सो दॅट्स व्हाय आय जस्ट राईट 1 1 0 1.
ओके ओके.
आता जर Q6 असेल, आता Q6 28 70 पासून 28 ला एकच पाथ आहे.
0.
त्याचं वेट काय 0. सो माय कोड इज 0. दॅट्स इट.
Okay, sir.
So in this way you can able to just calculate the particular path. So जे काही रेक्टँगल्स आहेत, जे एलिमेंट्स आहेत ते आपल्या रेक्टँगल ब्लॉक मध्ये आहेत आणि जो नोड एलिमेंट आहे तो आपल्या राऊंड रिक्ट मध्ये आहे. सो राऊंड रिक्ट मध्ये इंटरनल नोड्स आहेत आणि जे काही लिफ नोड्स आहेत ते आपल्या रेक्टँगल ब्रॅकेट्स मध्ये आहेत और रेक्टँगल स्क्वेअर मध्ये आहेत. So we have to just calculate the path from root node to the square. Okay, so whichever the elements which are happening, so we can able to assign the weight for each and every edge which is happen inside your particular tree. Okay, so left part ला असेल तर 0 असाइन करायचं, राईट पार्ट ला असेल तर 1 असाइन करायचं. ओके, आता इथं जर लेफ्ट पार्टला आहे तर आपण 0 असाइन केलं, राईटला आहे तर 1 0 1 0 1 0 1. ओके, सो जर 4 काढायचं असेल तर काय येणार इथं 1 0 0. 6 काढायचं असेल तर 1 0 1. आता 15 काढायचं असेल तर 1 1. आता 8 काढायचं असेल तर 0 0. ओके, सो इन दिस वे we can able to just move inside our Huffman. आणि after Huffman tree कसं करणार, तर just considering these particular factors. ओके, सो पहिल्यांदा काय करायचं, तर हे दोन एलिमेंट आणि हे दोन एलिमेंट घेतले. ओके, सो 6 4 6 10 8 9 17. आता इथं 4 आणि 6 लेफ्टला काय, तर लेफ्टला कुठला एलिमेंट असतोय, जो लहान आहे तो लेफ्टला असतोय, जो मोठा आहे 8 9 17. ओके, आता काय करायचं आहे, तर 15 ऍड करायचं. सो 15 कुठे येणार, आता 17 पुढे तर येणार नाही, 17च्या इकडे येणार. ओके, ह्याच्यामध्ये येऊ शकते. ओके, सो मी ह्याच्यात ऍड करणार इथं 15. ओके, सो दोघांची टोटल काय झाली, तर 25 मध्ये मला काय करायचं आहे, हा नोड क्लब करायचा आहे. सो 25 ची व्हॅल्यू कुठं, आता ह्याची व्हॅल्यू ह्याच्यापेक्षा लेस पाहिजे, म्हणजे लेफ्टला पाहिजे. सो आय कॅन जस्ट ऍड ओव्हर हिअर. आता त्याच्या अगोदर काय पाहिजे आपल्याला, तर 8 9. सो 8 9 ह्याच्यापेक्षा लेस पाहिजे, सो लेस आहे. सो आय कॅन जस्ट ऍड इट. ओके, सो ह्याच्यानंतर ह्याची दोन बेरीज काय झाली 42. आता 42 आपल्याला काय करायचं आहे, हा नंबर 28 ऍड करायचा. सो 28 कुठे ऍड करणार आता, तर ह्याच्यापेक्षा पुढे आहे, पण हे डायरेक्टली रूट नोडला कनेक्ट करू शकत नाही. सो आपण लेफ्ट साइडला ऍड केलं 28 आणि त्यांची जी बेरीज आहे ती 70 आपल्याला रूट नोडला आहे. क्लिअर. आता समजा मी जर 28 इथं ऍड केला, आता कुठला आहे 28, आता ह्याच्यापेक्षा इथं आहे, तर एकाच नोडला 3 नोड ऍड होणार का, रूट नोडला नाही, 2च नोड ऍड होतात. Okay, so that's why we are not able to add over here. That's why we just added over here, and we can just combine this. Okay, so such logic we have to just apply while designing the Huffman tree. And once you design the Huffman tree, you simply assign the weights 0 1 0 1 0 1, and we can able to just continue with that particular weights. Okay, so this is the logic which we can able to add in our program. Clear?
Yes, sir.
Yes, sir.
Okay, so you can just read the particular contents and try to solve that particular example again. Okay, so whenever you are reading the particular contents, so already PDF is shared to you. At the time of solving, you just consider the example and solve it by your own logic. Again, you can just change the numbers. आता इथं आपण काय केलंय की 15 ऐवजी 32 घ्या, 28 च्या ऐवजी 48 घ्या आणि बघा काय कसा ट्री चेंज होतोय ते, आणि how we can able to add the particular contents inside the tree. Okay, सो लॉजिक काय आपलं, तर जो काय रूट नोड असेल, आता हा रूट नोड आहे 70, तर लेफ्ट पार्ट हा लेसच पाहिजे आणि राईट पार्ट हा ग्रेटर पाहिजे. ओके, सो ग्रेटरचं जर ह्या पर्टिक्युलर भागात लेस एलिमेंट, ह्या पर्टिक्युलर भागात ग्रेटर एलिमेंट. ओके, आता 28 लेस आहे, 42 ह्याच्यापेक्षा जास्त आहे म्हणून इकडच्या भागात आला. आता सेम लॉजिक इथं आपण अप्लाय करायला लागलो, 70 लेस आहे, 25 ग्रेटर आहे. अगेन सेम लॉजिक आपण अप्लाय करायला लागलो, 8 लेस आहे, 9 ग्रेटर आहे. ओके, सो आपण रिव्हर्स डायरेक्शन जातोय, त्यामुळे दोघांची बेरीज आपण करत होतो. ओके, सो लेस greater again addition, less greater again addition, less greater again addition. Okay, so in this way you can able to design the particular tree by in the down to up direction. Okay, so in this way you can able to just design the particular tree efficiently by using this particular way. Clear?
Yes, sir.
Okay. So just
Yes,
write
sir.
down the questions related to the first chapter. So this is sort of which type of the questions that can be just appeared in the exam. It is sort of question bank. Okay, so it will just cover all the questions, all the type of questions which are just coming inside the exam.